Hello everyone. Let's start the next set of 5 questions, that is question number 21 to 25, organic part of the June 2021 CSR question paper, right. So, the first question says the major product formed in the following reaction is, this looks very simple. You are having alpha beta unsaturated ketone and you are having Gilman's reagent R2CuLi. Okay, R2CuLi is not very ionic, it's quite covalent, I would say. So, you are having 2 methyls on copper. So, it is more about a orbital interaction than charge-charge interaction, and then you are having methyl group which is away from the viewer, and is asking what will the product form, cis 3,5 dimethyl cyclohexane, which is chiral or trans or cis or chiral achiral. So, let us first understand this. Now, on this molecule there are two electrophilic centers where nucleophile would attack. It will be attack either at position 2 or position 4. See, position 2 has lot of positive polarity. So, it will undergo what is called a charge-charge interaction, something like if RMGX would have been there. RMGX is almost like ionic, it is a lot of negative charge. So, it will go and attack here, though this is not favorable, but it is charge-charge interaction, so much positive negative charge that it will go and immediately attack on the carbon which has a lot of positive polarity, because it is directly attached to oxygen, and that too there is a pi bond. So, this whole cloud, pi bond is like cloud, whole cloud is taken away by oxygen. So, a lot of positive polarity by on this carbon, but this leads to unstable, thermodynamically unstable product, because what happens is once you get this, you are forming a carbon carbon single bond, but losing a carbon oxygen pi bond. Now, carbon oxygen pi bond is very stable. Okay, I would have given somewhere values. Let me show you if I have the values. Yeah, see, carbon carbon single bond gives you sigma bond when it is formed 81 kilocalories per mole. When double bond is formed, that is pi bond is formed, you get extra stability of 64. Of course, we know pi bond has less bond energy. But when you come to carbonyl group, that is very interesting. In carbonyl group, single bond sigma bond is 79, but when you are having carbon oxygen, sorry, this is by mistake, this is carbon oxygen. Okay, so carbon oxygen, when you are talking about the pi bond, you are getting extra 94. So, because lot of ionic character comes apart from the covalent character, covalent bonding, and therefore it gets more stabilization on pi bond than sigma bond, and therefore it is not at all favorable that you break a pi bond carbon oxygen and form a single bond carbon carbon. So, but that is what happens because it is charge interaction. But when you are having R2CuLi, so that is a Gilman's reagent. Okay, so here it is, it's not a lot of positive charge, it's all about interaction. So, these lobes are much larger because it's not attached directly to carbon. Okay, so this lobe is large, this lobe is large, so a lobe interaction occurs, and this gives thermodynamically favorable product also, because here you are forming carbon carbon sigma bond and with loss of carbon on carbon pi bond. So, that's what happens, and you get the product. All that I have said is written here, maybe I will go once again slowly with it. Yeah, so basically attack happens here. I did not write mechanism or what. So anyway, I'll tell you. So this goes up and you get here, and what you will get product is basically this. What you get product is basically this. You get O minus, and you get here, and you get R here. Okay, you get R here. Now once this, when is coming back during the workup, because you in workup you add water, it picks up proton from water and you get back ketone, and you are getting R at position number 4. Okay, you get back ketone and you get R at position number 4, and that methyl group which was there away from the viewer, that remains intact. Now we have to know where this R has come. Is it towards the viewer or away from the viewer? That's the question, right? Now you please understand, cyclohexane, hexene, they are always tried to be in chair conformation. This is the conformation which is there. So this, you understand, this hydrogen is coming out of the board because trigonal planar. Okay, sp2 hybrid, this is also coming out of the screen, you can say something like that. Okay, and you are having two p orbitals and you are having C double bond O. Now if it attacks from top, what happens? See, if it attacks from top, no, this part will go up. This carbon bond is there, no, this will go up and you get something like that. You get something like this. You get Me on top. Okay, you get Me on top. And but what happens is this conformation, what happens now? You see, this part is down, this goes up, and then another one up, and then down. You get like this twist boat conformation, highly unstable conformation. It will never go through something like this. Okay, but what happens if attack occurs from down? So when it attack happens from down, this goes, so you understand, wherever it is attacking, that carbon gets pulled down that side. So if it was up, so this carbon gets pulled up. If it is from down, carbon gets pulled. So it is coming pulled down. So what you are getting here is this methyl on down, you are getting a chair conformation. Please understand, see the numbering, you will appreciate this. This is carbon number 5, this is carbon number 5. Okay, so methyl is down, H is up, methyl is down, H is 5. 4 is here, 3 goes down. So that's what 4 is here, 3 goes down, and you are having methyl at the equatorial position, very stable. Initially also it was an methyl, here also is methyl, and then you get something like this, and then this goes and picks a proton. So what happens? This methyl is below the plane, so you write it away from the viewer. This methyl is also below the plane, so again you write it away from the viewer. And so what you are getting is, you are getting like this product. So you can see there is a plane of symmetry running in between, so it is a meso compound. Okay, so I hope you know how to draw this. Once again, let me explain you this part. How do you draw this? Okay, somehow I have not drawn very properly. I should have drawn something like this. Okay, should have drawn something like this. That makes much more sense, I would say. Yeah, something like this, you see. So this is the double bond, and this is next carbon where pi bond is there. Very clearly you have drawn C double bond O. Then what happens? Next to that nothing is there, so next to it nothing is there, and then you come to this where methyl is away from the viewer. So when it is away from the viewer, so you have to draw it below the plane, and that means H is toward the viewer, so it has to be drawn above the plane. So that's how you have drawn this, and this is your structure. Okay, so when Me is down, H is above. So it was not very neat diagram, but H should have come more planar. Okay, uh, that's it. So your answer is option C, cis 3,5 dimethylcyclohexane, which is achiral. What I have said I have written. I'll go once again slowly. Please read through it, and yeah, read through it slowly. Pause it if you need. Yeah, let's go to the next question. Question number 22. It says the correct sequence of mechanistic steps involved in formation of product in the reaction is. So you are having this molecule, you are adding tin chloride. You know, tin chloride is a SnCl4 is a Lewis acid, and you are getting this product. So what are the it is asking what is the steps sequence. So is it first Prince cyclation followed by oxonium ion or pinnacle rearrangement? First of all, this Prince cyclation not very common reaction. Okay, luckily I know it because when I was doing my postdoc in IIT Kanpur, this was my project. I have done a lot of work on Prince cyclation, but I will explain you. Hope you will all remember this. Okay, so once you see what comes to your mind first thing when you look at this molecule? When you look at this molecule very clearly, there is a acetal. Acetal always looks like this. You are having on same carbon, you are attached with two oxygens. That means this part was diol, this part was diol, and this part was aldehyde or ketone, depends. Okay, so here what it is like that. So this part was aldehyde, this part was aldehyde, and this part was diol. They both react, you know, they both react here, and basically H2O is lost. Now these acetals are very labile. They're quite stable, but they're labile. If you have to put in acidic media, they're very labile, but in basic media they are wood solid, I would say. You cannot cleave it. So acetals a good protecting group for carbonyl or diols, whichever way you look at it. Okay, so but you are putting SnCl4 very clearly. So SnCl4 will go and coordinate with one of the oxygen because they are labile. That's how they break it. So of course the first step has to be formation of oxonium ion. Very clearly I know this answer. I would not have looked forward further. I would have ticked off this thing because there is no other option. Anything can happen before formation of oxonium ion. Okay. So this goes and forms oxonium ion, and then you know acetal how cleavage occurs. It is it is always the attack is intramolecular. Please remember this. It cannot happen that water goes and attacks. First oxygen, this second oxygen gives lone pair electron, this opens up and you are getting this, and this is where the damage has happened. Otherwise normally this would have been followed by addition of water and then deprotection would have occurred. But because what has happened here is you are having this OSN bond. Okay, now OSN bond is nucleophilic. Sigma star, sigma will be nucleophilic. It is nucleophilic sigma bond. Why? Because tin is having negative charge. It is tannate. So whenever you are having negative charge, all the bonds to the tin, they become nucleophilic. So this can also attack, but more than that, this pi bond, because whatever may be the condition, pi bond is definitely more nucleophilic than your sigma bond. So even though it is a more nucleophilic sigma bond, but pi bond is what will attack, and even if this attacks, it will form the same thing. So this pi bond goes and attacks on this carbon. Okay, because of this pi bond, reaction took another way, and apart from that, of course, they would have avoided water in all conditions. So what happens? This goes and attacks here, this comes here, and you are getting this product. Okay, so this is called as Prince cyclization. So Prince cyclization is you are having carbonyl. Carbonyl you protonate it. So generally you can use some BF3 kind of stuff, or sometimes even very strong acid you can use, and then alkene goes and attacks it. That is what is Prince cyclization. That's how we cyclize it. So second step is Prince cyclization. And third step, what happens? So third step is this is sigma bond is nucleophilic, as I said before. This comes up here and this comes here. So this is a pinnacle rearrangement. We know about pinnacle. When you are having diol, then you protonate one of them, and then this, that's what is happening here. It's just like it's protonated. So this comes down, this goes and attacks here. So this is pinnacle rearrangement. So of course the answer is option number C. Moving on to the next question. The major product A and B in the following reaction sequence are. So you are having what is called as DMAP. It's a very important catalyst we use when you are doing nucleophilic substitution reaction. So generally we carry out in pyridine because pyridine helps in nucleophilic substitution reaction, and we use DMAP. DMAP we don't use like 1:1, it just uses as catalyst. It helps. How it helps is basically it pumps electron. Okay, it pumps electron like this, and it increases electron density at alpha carbon. And then it comes back, and then it also increases electron density on the nitrogen. So nitrogen will go and attack, and so that leaving group leaves, and you get positive charge on nitrogen. This becomes good leaving group. Again something will attack and this leaves. So DMAP is very important reagent. Please remember it. And right now I would suggest you, please open Google, type DMAP. You learn about it so that it will stay with you longer time. Okay, and you are adding here CF3CO, so it is anhydride. Okay, acetic anhydride, but trifluoromethyl acetic anhydride. Okay, so what happens? What is the product formed? So first product A and then second product B they are asking. So what happens is so you can go through it, whatever I said, no, it's written here. Yeah, now what happens? But attack has to have to occur on carbon. Now carbon is more nucleophilic than nitrogen because nitrogen electronegative, more electronegative than carbon. So it holds the electron closer towards itself than oxygen than carbon. So carbon lobe is larger than the nitrogen lobe. Nitrogen lobe is also quite large. Okay, compared to oxygen, nitrogen lobe is very large, but carbon's lobe will be of course larger, and therefore carbon is more nucleophilic. So rather than nitrogen attacking, this carbon goes and attacks here and you get this and you get this. This is your A. Next what happens? Next you are adding NH2 NH2 HCl. You are adding hydrazine and HCl. So HCl is acidic. So of course this will go and take and you get a proton, and then hydrazine attacks. You know, it's very simple. Whenever you see such things, it will be basically loss of water. So hydrazine H2O. So you can ask directly why HCl is needed. This is a very good question if you have thought about it. HCl is important because carbonyl carbon is not electrophilic enough that nucleophile can easily attack it. So we always add acid, okay, Lewis acid, or here we are adding strong acid, so that oxygen goes and attacks on this HCl proton and you get a positive charge. Now oxygen has become very electronegative, so that this will go and attack here, and all that happens, we need not know about so much mechanism, but basically hydrazone is formed, okay, H2O is lost and you get the hydrazone. Yeah, this is what it is, it forms the hydrazone. Then what happens? Now two things are there, either NH2 can attack here or NH2 could have attacked on this carbon. If it attacks here, what happens? You get a positive charge on nitrogen. Nitrogen picks a proton and you are having one hydrogen. Now in the next step, to gain the aromaticity, if you remove this proton with some base, okay, base will always be there, something like water itself will act as a base during workup. This, if this comes, you cannot gain back aromaticity because H minus cannot be lost, okay, H minus cannot be lost at all. So if this undergoes reaction like this, product becomes unstable, you cannot get back the aromaticity. Of course attack will not happen on this carbon, attack will happen on this this carbon. So let us see what happens. Okay, so this attack happens here, this comes here and you get a negative charge, you get a positive charge here which is picked up by this dimethylamine part, and then this is very simple, this negative charge is formed here because it is stabilized, you can see here nitrogen stabilizes the negative charge better, and then this negative charge again goes and attacks here, negative charge goes and attacks here, and this one leaves and you are getting the product. Okay, so that's it. So this is your product form. So answer is option A. Okay, next question. Given the specific rotation of hexane is plus 22, okay, so they are saying for the S, okay, S, you know, it is capital S, so it is absolute configuration is plus 22. It is saying enantiomer selectivity is 98%. Now it does not say it is for capital R or capital S, that is what we have to find out. It is just saying that for capital S it is plus 22, and if enantiomer selectivity is 98%, what will be the specific rotation? So two questions they have put together. First they want you to find out which one forms more, R or S product. In this product, R or S, which one forms more, and then they want to know, this is simple question after that, that what's the specific rotation, find out the rotation, okay, optical rotation, that's what they have asked. So so when it says enantiomeric excess is 98%, that means one of the enantiomer is 98%, other is 2%, 2 plus 98, 100, but we don't know which one is in excess. So now this is called as chiral auxiliary group. We are using this is used for aldol condensation as a chiral auxiliary group, because this is kind of handle, okay, extra group they have put, so that this will just help in getting stereoselectivity and this will be removed again. So it is auxiliary. Auxiliary means, you know, extra handle they provide you, which is not needed actually, but it's needed for this carrying out a reaction to get stereoselectivity, and then the reaction occurs. So first step is, of course, whenever you see such things, H2O will be lost, condensation reaction is a kind of hydrazine, so hydrazone will be formed. Now what happens? See, you are having methyl and this OMe is towards the Weber and two hydrogens are there, very clearly tetrahedral will be maintained. Now you are using LDA as a base, correct? You have used LDA as a base. LDA is a very powerful base. Also LDA specifically, please understand, if they use LDA means LDA is used for as a bulky group, okay, it's a very bulky base, you can see 2 isopropyl group are there. So it will pick up proton from the behind, not from the front, because front you are having this extra handle. So it removes proton, you get negative charge and Li positive. It's almost ionic, you know, but it's good to show it like that. Now what happens? Now lithium is electropositive and very small in size, you know, it comes on the top. So it forms a bond with oxygen. So what happens? So this will go and coordinate with the oxygen and you get something like that. You get bonding like this, and then what happens? This goes and attacks here and this leaves here, and you are getting this product. So after that you do ozonolysis and then just you remove this group and you are getting this. So once you find out what happens is, this is S configuration. Okay, this is simple, we need not deal so much. This get first, second and third, so it looks like S. It is S, hydrogen away from the viewer. So specific rotation will be 98% of S plus 2% of R. So 98% of plus 22 plus 2% of minus 22, and that's what you get as 21.12. Thus the answer is option B. We will do only 4 questions for today. Thank you very much.